All right, we're here in section 4.8. You can see we're going to look at compound interest, which will give us some nice applications to the exponential and logarithmic functions that we've been working with, okay? And what better application than money, right? You probably already have a concept of interest conceptually built up. There's good interest and bad interest. Good interest would be in investment scenarios where you're, let's say, putting money into a savings account or a CD at a bank. The bank is going to give you some interest, some extra money over time for allowing your money to sit in their bank. Okay. Bad interest would be whenever you are borrowing money from a bank or a lender, like for a mortgage, a credit card, car loan, something like that. They're not just going to give you the money up front for free. You have to pay it back to them over time, and in doing so, they're going to charge you some interest. Okay, so that's the type of interest that we would like to avoid. There are two types of interest: simple interest and compound interest. So let's look at simple first. Let's say you have a principal of P dollars that's being borrowed or invested for a period of T years at a yearly interest rate R, which will need to be expressed as a decimal. Then your interest I charged or gained is going to be found with the formula I equals P times R times T. So basically what this is saying is to calculate the interest charged or gained, all you need to do is take your initial amount of money, multiply it by your yearly interest rate, and then multiply it by the number of years that this is going to take place over. Okay. Um, then we have compound interest. Okay. Now, compound interest is the interest that you want to take advantage of in an investment scenario because it's interest paid on principal and any previously earned interest. So basically what we mean by that is you put your money into a bank account, let's say, and over a certain amount of time, they give you some interest to tack on to your original principal. So that means your balance in the account is a little bit higher now. And then they'll calculate interest a second time on the new higher balance, which means you'll get a little bit more interest, okay? And if you do this repeatedly over years and years and years, you end up gaining more interest than you would in the simple interest scenario, okay? So compound interest, it's a beautiful thing. We have a formula that we can use to find the value of an investment in a compounding scenario over a certain amount of time. So the amount of the investment would be A. It's going to be after T years due to a principal P invested at an annual interest rate R that's being compounded N times per year. It can be found with the formula A equals P times 1 plus R over N raised to the power of N times T. So the first thing I want you to notice is this is an exponential equation, okay? Obviously, with the fact that we have a power of nt built into it, okay? The next thing I want you to notice is what's happening to your interest rate here. Your annual interest rate is being divided by n, which is the number of times you're compounding in a given year. Okay, so basically we're taking that interest rate and instead of just finding it, once a year or using it once a year, we're breaking it up over multiple times in the year. So you're actually getting a little bit more money up front before the year actually ends. Okay, so let's apply it to the scenario below. We have a credit union paying interest of 8% per annum, which just means yearly, compounded quarterly on a certain savings plan. If $1,000 is deposited in such a plan and the interest is just left to accumulate, meaning we don't add any more into it, how much is in the account in 1 year? Okay, so let's identify the different pieces of information here. This 8% per annum, that's my R value. I want to express it as a decimal. Okay. If I'm compounding quarterly, that means 4 times So N equals 4, and then my initial deposit was $1,000, so that's my principal. Okay. All right. So, and then of course, T is just 1 year here. So we only want to know how much is in the account after 1 year. So the amount in the account after 1 year would be equivalent to my initial amount of 1,000 that's been invested times 1 plus my interest rate divided by 4 raised to the power of 4 times 1. And that's simple enough. You can punch that all into your calculator and you should end up with a value of $1,082.43. So notice this is giving you the value of the account at the end of the year. It's not directly giving you the interest that you got in a year's time. So that's simple enough to do, though. Just take this final amount and subtract it by the original principal, and you can see we are accumulating $82.43 of interest in this 1 year. Not too bad. All right, now notice we could have used our simple interest formula 4 different times to find this same value, but who wants to do 4 separate calculations when this will let you do it, with just one calculation? All right, moving forward. Now let's get into a really intriguing concept. It's the idea of continuously compounded interest. All right, imagine a bank that would allow you to put money in to an account, and the moment that you put it in, they give you some interest, okay? And then the interest is left to accumulate an infinite amount of times. So that's the idea of continuously compounded interest. The amount A after T years due to a principal P invested at an annual interest rate R compounded continuously is found by the formula A equals P times E to the power of RT, okay, where E is that exponential value of approximately 2.718. So here's a nice application of where that value of E comes up, okay? I call this the shampoo formula. The reason is, I'm not sure if they still sell this, but back when I was growing up, there used to be a shampoo that was pretty popular called PERT, P-E-R-T, and notice the equation, of course, spells the same word, P-E-R-T, okay? So you're going to use this formula anytime you see the word continuously along with compounded. If you don't see the word continuously, then stay away from the shampoo formula, okay? Now, I want you to understand continuously compounded interest, it's not a real thing. No bank is ever going to give you an infinite amount of interest over time. But if nothing else, it gives us a nice threshold of the highest amount of interest that we could ever accumulate for a given principal, okay? So what's the amount A that results from investing a principal P of $100 at an annual rate of 6% compounded continuously for a time of 1 year? Well, I see that word continuously. I know to use the formula above. So A is going to equal my original amount of 100 times E raised to the power of 0.06 multiplied by 1. All right, now remember E is programmed into your calculator, so this should be another easy one to punch in. If you do so correctly, you should end up with $106.18. Okay, so if nothing else, what this tells me is that the most amount of interest that I could ever earn for a $100 investment at a 6% interest rate in 1 year's time would be $6.18. I'll never be able to earn more than that. Okay. All right, second problem here. How long will it take for an investment to double in value if it earns 5% compounded continuously? All right. So the question here is, how long will it take? That means t is unknown here. Okay, so I'll need to be solving for t in my problem. The only value I'm given directly is 5% for r. I'm told this is happening continuously, so I know to use that shampoo formula, but they don't tell me the amount of the original investment. That doesn't really matter, okay? All that matters is I know that it needs to double, okay? So if my original amount is the amount of P, then I'm going to multiply that by E raised to the power of 0.05 times T, and I know that I want this whole thing to result in double the original, so I'm going to set it equal to 2P, all right? So this just is proof that P is arbitrary, because what I can do is divide P from both sides, and I end up with a nice little exponential equation to try to solve for T. All right, now this is an exponential equation where I'm not going to be able to write the bases in terms of the same value, so I need a logarithm. I'm going to take a natural log on both sides, and I would definitely use natural log this time. Okay, now the reason for that is because the natural log has a base of e, and recall we had a property that says log base a of a to the power of r equals r. All right, well, that's exactly what I have going on the right side of this equation. So I can say that the natural log of 2 is really just going to equal 0.05 times t here. Okay. And now I'll solve for t by simply dividing out 0.5 on both sides. Natural log is, of course, programmed in your calculator, and you're going to end up with t being approximately 13.86 years. So it's going to take you not quite 14 years in order to double your investment, okay, no matter what the investment is. Okay. All right, last thing to talk about would be effective rates of return. An effective rate of interest is the equivalent annual simple rate of interest that would yield the same amount as compounding after 1 year. Okay, so basically what we're saying is you have an interest rate, a compound interest rate that'll give you a certain amount of money. What would be the simple interest rate that gives you the same amount of interest after 1 year? And this simple interest rate, if you think about it, it's going to have to be higher, a higher value than the compound interest rate, because simple interest is only calculated once in a year, right? Whereas the compound is happening multiple times. So if you want the same amount of interest in the end, you'll need a higher simple rate of interest, right? So look at the scenario here. We have January 2nd, 2007, $2,000 was put into an IRA account that will pay interest of 7% per annum, compounded continuously. What is the effective annual rate of interest? Okay, so what we need to do first is find the amount of interest that would be gained in the compounding scenario. Okay, now this is continuously compounded interest, so I'm going to have to use my shampoo formula. All right, so we're putting $2,000 in, multiplying that by E raised to the power of 0.07 for my interest rate. And notice I kind of skipped over this, but effective rates of return are always over a period of 1 year. So my time here is 1, okay? And that is going to amount to $2,145.02. So that means the amount of interest that's been gained in this compounding scenario is $145.02. Now all I need to do is take that interest value and substitute it into my simple interest formula that we looked at the very beginning of the lesson. Okay, so that would be I equals P times R times T. I know I want my interest to be $145.02 on an initial investment of $2,000. What's the simple interest rate needed to do that in 1 year's time? Clearly, we're just going to have to divide by 2,000 here to solve for R. You're going to get a decimal, which ends up being R equals 0.07251, which we want to think of that as a percentage. So my effective rate of interest is 7.251%. Okay. Notice that is a slightly higher interest rate than in the compounding scenario as we discussed at the beginning of the example.